In this screencast, we're going to talk about the rank of a matrix, the span of some columns of a matrix, and the ideas of linearly dependent and independent. We're going to do it with two examples. We'll start with this matrix right here. When you look at a matrix, the rank is the number of pivot columns. So I've already reduced both matrices, and notice that the number of pivots, I'll circle it in each. Here the number of pivots is 2, so here we say the rank equals 2. Notice that the rank is less than the number of columns. One of the columns, this column right here, is not a pivot column, but over here the rank is 3, which is the number of columns. We'll discover that the rank equaling the number of columns actually tells us a lot of information about the vectors in the original matrix. So we're going to take this matrix and we're going to draw the vectors in 3D. We've got an x-axis, a y-axis, and a z-axis. Well, in the x direction I need to go 1, so think of this as the vector 1, 0, 0. We'll go 1 in the x direction. For this, before we move on, I want to look at what is the span of a vector. The span of a vector is all possible linear combinations of that vector. Well, I can take that vector and multiply it by any number at all. So I could take a times by the vector that, where a is any real number at all. Well, really what that means is I could double it, I could triple it, I could turn it around. I'm really getting all the vectors on the x-axis. And that is precisely what the span of that vector is. The span of a vector is just a line containing that vector. So now we'll look at the second vector. We've got a 0, negative 1, 2. Negative 1 in the y, 2 in the z. There's our vector. If I just look at the span of that vector, I'll end up with a line again. But what happens when I take the span of two vectors? Well, if the two vectors lie on the same line, then you won't get anything in U. If the two vectors happen to both be on the same line, then the span of the two vectors would be just the same line. But in this case, the two vectors are on different lines, which means those two vectors, well, I could take that vector plus this vector. So using the parallelogram law of addition, I get out a vector right there. Or I could double that one, or I could double this one. It doesn't matter. But notice, I'm getting a plane. This is a plane of vectors. It's a two-dimensional space. It's something 2D. That actually has to do with the rank, and we'll see that in just a bit. Let's now try and add the third vector in. 3, 2, negative 4. 3 in the x, 2 in the y, and negative 4 in the z. Here is our vector. Now, comment. Notice that it's 3 in this direction, and if you take this vector and turn it around and double it, out pops that vector. So 3, 2, negative 4 actually is already in the plane spanned by those two vectors. So 3, 2, negative 4 is already in the plane. Well, actually, REF helps us understand how to connect this vector as a linear combination of these. If you take the 3 and the negative 2 from REF, so I'll grab the 3 and the negative 2. Now I'm going to take the vector, the column, the pivot columns, and I'll write them next to these numbers. 0, negative 1, 2. If you take this vector and triple it, and take this vector and times it by negative 2, what do you get? 3, 2, negative 4. That's precisely the non-pivot column. So non-pivot columns are linear combinations of pivot columns. That's a key fact we want to focus on. Non-pivot columns are linear combinations of pivot columns. Well, so if somebody were to ask me what is the span of the space formed by the three vectors, 1, 0, 0, 0, negative 1, 2, and then 3, 2, negative 4, I would have to say, well, adding this third vector in did nothing. If I remove it, I still end up with the exact same thing. This vector depended upon those two. So 3, 2, negative 4 depends on the pivot columns. This leads precisely to the idea of linearly dependent. One vector is a linear combination of the others. Notice that 3, 2, negative 4 is a linear combination of the other two vectors. So if somebody asked me, are these three vectors linearly independent, I would have to tell you, no, those vectors are dependent. The third one depends on the first two. The third one is already in the plane spanned by those first two. So this third one doesn't contribute any new information to the span. It only is something that's already in the span of those two vectors. Notice that because the rank was 2, which is less than the number of columns, that the non-pivot column depended upon the pivot columns. Hence, if the rank is 2 and the columns is 3, then these three columns are dependent. So now let's jump to this other example. Here the rank was 3. Well, the two vectors in the first two columns are the same. I just changed the third vector. I'm going to draw now the vector 0, 0, 3. Is the vector 0, 0, 3 in the plane spanned by those two vectors? Well, I'm going to put my hand in as a plane, and the vector 0, 0, 3 comes up through. Notice that it is not in any way, shape, or form in the plane spanned by the first two columns. So when we RREF, we discover, hey, each of these vectors contributes a new direction to our span. None of them is a linear combination of the others, so here we say they are linearly independent. And that is precisely what we have, linearly independent. None of the vectors is a linear combination of the others, or every column is a pivot column. That completes this way.